So do you want to talk a bit about yourself and what your subject is about?
Sure. So I'm Professor Kevin Otto. I've been at Melbourne now for about 6 months or so. I don't know. But I'm interested in design, manufacturing of mechanical devices, electromechanical sorts of things. I do a lot of research in designing systems so they don't fail, designing systems so that they're of high quality, low variability, these sorts of things. So this is a course, Design and Manufacturing Practice. So it's a project course. So this is design it, build it, and prove it works. And if it doesn't, make it so it does. It's a subject on how to design things so they can be easily manufactured. More easily means less potential for mistakes, and more easily assembled. After you have the parts fabricated, then you got to put it together. And there's good ways to assemble things, and there's difficult ways to assemble things. And anything that's difficult is more prone to fail. There are examples all the time in the news about ostensibly engineers who have failed to do a good job at this. Everybody loves a Tesla. Boy, I'd love to drive a Tesla, right? Wouldn't that be great, right? When the Tesla Model 3 launched, it was with huge failures, okay? They were having big delivery problems meeting demand. And when you're having delivery problems meeting demand, it means that some of your parts are having a hard time being brought in to be assembled, which means some of the parts are hard to manufacture. And that's exactly what was going on with the Tesla when they launched. They thought they had the battery packs figured out. Turns out they didn't. Some of the things that they thought they could hand assemble were too hard to hand assemble inside the packs. So, I'm picking on Tesla. The biggest failure, most costly single point failure, Airbus, the A380. All right. They had a problem with how they were designing wire bundles. And turns out a lot of them all of them that they designed were all too short. All right. And how did that happen? All right. So these things happen all the time because people aren't thinking enough about, ensuring their designs can be manufactured. So that's what this course is about, learning how to design parts so that they can be, machined, fabricated, molded, sheet metal formed, these sorts of processes, and then better ways to assemble them.
So what type of student would this subject be suited for?
So it's a hands-on project. Mechanically, I won't say mechanically trained. I won't say that you have skills in machining, none of that. I mean, it's sort of what we learn here. The first week, there's a 6-hour refresher course on SolidWorks, because that's what we're going to use, all right, to design parts, CAD/CAM, to generate CNC code so that the parts can be, CNC machined. So we're not going to get into, mechatronic, Raspberry Pi sort of codes or anything like that. It's mechanical. So keep that in mind. So I'll also say it's a project course. So what's the project? This year, what we're going to do is in teams of 5, we're going to redesign, I'll say, we'll redesign our own 3D printers. What we want to do is design it for production. All right. So we're going to take the Prusa 3D printer, which is a great machine because it's all open source. You can download the part files and, 3D print your own machine and buy the parts and do it yourself. So that's what we're going to do. We're going to take parts that are 3D printed and redesign them so that they are easier to be machined. All right. We can't have certain shapes. If we're molding it, fewer undercuts, where's the parting plane, these, draft angles, all these things start coming into play. So that's what it's about. We're also going to look at sustainability a bit through the lens of this course, which means how hard is it to disassemble at the end of life? All right. If you want to replace a part and repair it? You know, do you have to get out precision micrometers to get it realigned and everything perfect? Or you just, you know, unscrew it and screw it back together? How difficult is it, right? So these sorts of topics we'll be looking at. We are not going to have students, you know, doing CNC machining. You're going to design the part in SolidWorks, and then we will review it and make sure that it's sufficiently machinable. And then we will hand the part off to a machinist, much as an engineer in reality in the real world does, and the machinist will fabricate it. All right, so that's how it's going to be. You will get back real parts, and actually, yes, you will do the assembly.
How does the subject contribute to the manufacturing specialization?
This is a project course. So, you know, in some sense, it's the theory courses on, you know, forming, machining, feed rates, you know, how fast, you know, cycle times and all that, you know, we do calculations and that sort of thing. This is going to be an experience around it. So, you know, it will bring to life that which you have already seen in other courses, or will give you context for if you see it again in future courses, you know, in manufacturing, let's say. There are some activities and theory that we will be picking up on. So this is where we get the design for assembly instructions in the curriculum. It's not anywhere else. The design for piece part fabrication, you know, how to design for something to be molded. So we're going to go over guidelines, you know, how to analyze this for you know, what's good, what's bad. We'll cover that. And then you're going to have to design the part. All right.
So,
yes.
But in the workshop, what do they do each week?
So the first half of the class is design. Weeks 1 through 7, design. Weeks 8 through 12, fabricate and test. Okay, and that's how it's going to go. So in your teams, every individual will design a part for CNC machining, will design a part for molding, and will design a part for sheet metal. So every team will get 6 parts machined and handed to them in replicates. All right, CNC machine. So it's going to be a little complicated because of dual delivery, blended learning, right? So it looks like right now, 1/4 of the class will be on campus and 3/4 will be off. The workshops, we will, week after week, just do the exercises that go into the report. So week 1, we're going to, it's one thing you have to turn in is, you know, for every part that's 3D printed, what would you use to replace it? You know, if you're gonna, you know, machine it, would you mold it? Would you what? Okay, we're gonna do that in week 1. Week 2, we're gonna do design for assembly in the class. So we're gonna work on fractions of these in the class, show how it's done, and you know, in some sense, the design report is stapling the workshop outputs together. Week 3 is sheet metal and molding. Week 4 is CAD/CAM, CNC machining. Week 5 is recyclability. Week 6 is tolerance stack-ups, so quality. So all that is part of what you have to turn in the individual design report. So we'll do them in the workshops. The actual build it, people off campus can't build. All right, so if you're not going to make it on campus, you're not going to build. So that may make it a little unfair to the on-campus students. So what's going to happen is I'm going to ask the on-campus students if they want to help build a unit. So if you want to build your own Prusa printer, come on in and you know, we'll do it in these weeks. Okay, so the actual assembly part, the off-campus students can't do. The inspection, the off-campus students can't really do. So that might be considered unfair to the on-campus students. So what we can do is, so I'm going to reform the groups, and we'll have, you know, 0 to 5 manufacturing groups of on-campus students. So maybe all the on-campus students will rebel and say, this is not fair, I don't want to do it. Okay, fine, you don't have to, it's voluntary. In which case, me and the two TAs will assemble 2 working units with the parts you guys designed. And we'll build them, and we'll provide the data, and the data will be available to the groups. Alternatively, maybe some of the on-campus students also want to build some units, in which case, with 25 students, that'd be up to 5 of them. So, we'll build them as manufacturing groups, reconstituted. They won't be the same as the design groups.
But how does this subject relate to the industry, or what kind of industry opportunities can students get from learning these skills?
Okay, so a couple things. First off, there is a machining consultancy firm called AINC that is working with us on this course. So this firm is a software development firm in mechanical design, and they offer services of taking your CAD drawing and giving you a report as to how easily it can be fabricated on CNC equipment, point 1. Point 2, how much it will cost, all right? And point 3, what you ought to do to make it easier and less expensive to be CNC machined. Second thing I'll say is this course was, partially designed with input from our industrial IAG, Industrial Action Group. Anyway, the advisory group, that's what it is, for the department. So, executive level, engineers at Boeing, at Asahi Beverage, from across our IAG, had input into this course. And one thing they've been resoundingly saying is, we want students that have more experience and skills at, designing for manufacture, and, being able to identify what's hard, what's not in getting things built.
And lastly, is there anything else you'd like future students to know?
So don't be intimidated by, I don't know any of this. Nobody knows any of this coming into it. All right. So that's not it. This is a place to learn it. All right. So, and what's exciting to me, so I've taught I've taught manufacturing, design for 20 years now on 3 different continents at 3 different universities. So, I know a lot about all it. What I enjoy out of this is the transformation that I see happening. First, I don't know this, and then by the end of it, people are comfortable with equipment in the shop, are comfortable with, putting things together, are comfortable with identifying, what's good and bad with particular designs for how it can be built. So that's quite good.